In review, a closed center locks the actuator in position, even in mid-stroke. Since pump outflow is blocked, the pressure relief valve must be in good working order since it will be routinely actuated. A tandem center also locks the actuator in position, even in mid-stroke. However, since pump outflow is routed to tank, the pressure relief valve will not be routinely actuated. A float center does not lock the actuator in position, but rather allows it to float freely, hence the name. This allows it to be repositioned by an outside force. Similar to a closed center, a float center does block pump outflow. The pressure relief valve must be in good working order since it will be routinely actuated. Finally, an open center does not lock the actuator in position, but rather allows it to float freely and be repositioned by an outside force. Similar to a tandem center, an open center routes pump to tank, thus saving the pressure relief valve the necessity of being actuated. Finally, I offer you this bonus round position known as regen. Not necessarily a center position, but rather a position of interest we'll examine in later lectures. Note the regen position routes pressurized flow to both actuator ports, A and B. Pause to consider the mind-blowing ramifications of such a connection. Would a double-acting cylinder with both cap and rod end at the same pressure extend, retract, float freely, or hold position? If you know how a double-acting cylinder works, and you have a passing familiarity with Pascal's law, you know the answer. All you have to do is think about it. If you're struggling with the answer, allow me to throw you this bone. Equal pressure, different area. Aha! We will return to this extremely cool application in later lectures, and until then, I expect you to remain in a state of cat-like readiness. I could continue to feed you more and more exceedingly difficult and confusing examples of directional control valve configurations, but it would serve no purpose since 1, by now I hope you're getting the picture, and 2, most likely the ones we discussed are the most common configurations you'll run across. Sure, there are others and truly unique configurations, but they're all variations on a common theme. Positions, ways, actuation method, which deactivated position is asserted by return springs offsetting or centering the valve, and whether or not the valve has any modifiers like manual overrides or detents. Let's call it good for now and continue on with the remaining contents of this lecture. If I employ odd configurations of directional control valves in later lectures, I'll try to take the time and point out the oddities. Absent our entire discussion is an examination of the components, the valve body, internal passages, spools, poppets, springs, and seals that actually make all this stopping, starting, and changing direction of fluid flow possible. Sure, we've examined some schematic symbols, but we've yet to look inside a directional control valve and see how it functions. Let's do this quickly before I cut you loose. Note, I'll need you to don both 3D and X-ray goggles, for we are about to explore the cutaway view of a directional control valve. Keep in mind the diagrams I am about to use are the simplest of simplifications, but they get the point across quite nicely. Our example cutaway view is the internal workings of a 3-position, 4-way, manually actuated, closed-center directional control valve with both a straight-through and cross-connect position employing a movable component known as a spool. A spool is cylindrical in nature with raised lands and lowered valleys. The main internal passageway machined into the valve body is also cylindrical in nature, similar to the barrel of a hydraulic cylinder. Inside the barrel resides the spool, also cylindrical in nature, machined such that there exists a tiny amount of clearance between it and the barrel. The spool and barrel do not make physical contact, but rather the spool rides on a thin layer of lubricating fluid. The lubricating layer between the spool and barrel also serves to seal the passageways. Sometimes dynamic seals like O-rings on the spool can be used to ensure that leakage is kept to a minimum. The raised lands prohibit connection, and the lowered valleys allow connection. As the spool slides the length of the barrel, the lands selectively block passages, at the same time the valleys selectively open others. The position of the spool, as dictated by the actuation method, therefore determines the position of the valve. Schematically, the closed center blocks all ports. The straight-through position routes P to A and B to T, and the cross-connect position routes P to B and A to T. As we'll learn, our cutaway diagram does the same. The cutaway view shows that the spring-centered spool blocks any connection between any ports P, T, A, or B when the manual lever is not actuated. When the spool is moved into the straight-through position by the manual lever, the valleys connect P to A and B to T. At the same time, the lands block P to B and A to T. In contrast, when the spool is pushed into the cross-connect position by the manual lever, the valleys connect P to B and A to T. At the same time, the lands block P to A and B to T. Our cutaway diagram therefore serves the same function as our schematic symbol. Here's all three positions simultaneously. Other configurations like tandem, float, or open center would require either different internal passageways, different spools, or both. I'll not go into these details since I'm hoping this simple example gets the point across quite nicely. Long story short, as the spool slides the length of the barrel, the lands selectively block passages, at the same time the valleys selectively open others. The position of the spool, as dictated by the actuation method, therefore determines the position of the valve. Very earlier in this lecture, I mentioned other symbols internal to the position boxes beyond dead-end T's and arrows. Additional symbols include, but are not limited to, flow control restrictions and check valves. Since we were just looking at a cutaway diagram, let's examine one of these modifications, flow control restrictions, right now. Flow control valves are restrictions or narrowing of a passageway. We'll examine flow control valves and flow control methods in later lectures. However, a simple modification of the spool allows this feature to be integrated into a directional control valve. Our previous example of a directional control valve had three clear and definite positions: closed center offering no flow, straight through and cross connect offering full flow. Consider, however, a spool with a triangular groove machined into the land. Such a spool, in addition to selectively connecting and disconnecting passages, also offers a means of varying the size of the orifice between passages. In this position, the spool blocks flow. If an operator only slightly moved the spool, only the smallest of passageways would be open in the groove, and flow rate in this direction would be minimal and actuator speed reduced. As the operator continued to push the spool in the same direction, the orifice would open more and more, and flow rate would increase. Finally, in the full open position, full flow rate would be achieved through the unrestricted path. Spools aren't the only moving internal components in directional control valves. Sometimes directional control valves employ poppets. Poppet-style directional control valves often employ the check valve symbol internal to position boxes. These are common in cartridge-mounted, solenoid-initiated, pilot-operated directional control valves. The operation of these style of valves is best explained using schematic symbols rather than confusing cutaway diagram. If you'll recall from the check valves lecture, available at the Big Bad Tech channel, a pilot to open check valve, as the name implies, acts just like a regular check valve in the absence of a pilot signal. One direction is free flow, one direction is blocked. A pilot to open check valve, however, opens in both directions in the presence of a pilot signal. Poppet-style directional control valves are basically one or more pilot to open check valves where the pilot pressure signal is provided by the solenoid. The solenoid is a type of linear electrical actuator similar to a cylinder with a rod. When de-energized, the solenoid doesn't push on the pilot fluid, and the pilot to open check valve acts just like a regular check valve. This example has two back-to-back pilot to open check valves. In the absence of the solenoid-initiated, pilot-actuated signal, both of them block flow and no flow path exists. This is functionally equivalent to a dead-end T. When energized, the solenoid pushes on pilot fluid and the pilot to open check valves both open. This is functionally equivalent to a bidirectional arrow. You may ask yourself, why didn't they just use dead-end T's? Wouldn't that be easier? Yes, but not only do the modified symbols clue you in on the internal construction of the directional control valve, they also keep non-technicians in a continual state of bewilderment. If this skill was easy, everyone would be doing it. Truly half the job of technicians is keeping non-technical peasants trembling in fear of your perceived black magic powers. Fear is an excellent motivator. Speaking of things that keep the peasants fearful, let's briefly examine pertinent data found on a directional control valve datasheet before we bring this lecture to a close. Directional control valves are typically specified as having a rated flow and a maximum inlet pressure. This might be written right on the side of the valve. The rated flow is a quick snapshot of the valve's performance at that specific flow rate. If you wanted to dive deeper into the valve's performance at flow rates other than the rated flow, you'd ordinarily consult the pressure drop for different flow rates performance curve or the operating limits performance curve. The pressure drop for different flow rates performance curve shows the typical restriction pressure drop created by the valve at different flow rates. If you're at a specific flow rate, ordinarily the pressure drop across the valve should be between the two curves. If you observe a different pressure drop across the valve might be obstructed or otherwise damaged. The operating limits performance curve tells you that the maximum inlet pressure actually varies as flow rate changes. The snapshot presented by the rated flow and maximum inlet pressure is a point on this curve. Additionally, valve specifications typically describe the amount of leakage at a certain viscosity and pressure condition, with the understanding that fluid with lower viscosity, i.e. thinner fluid, will leak more for higher pressure applications. Valve specifications also typically state the fluid compatibility, viscosity, and level of filtration required for proper operation. The valve seals must be assessed for compatibility with the temperature and fluid being used in your particular application. Most manufacturers offer a choice of nitrile, fluorocarbon, or special purpose seals. Finally, physical, connection, and cavity dimensions of the valve are often included in manufacturer datasheets. Alright, I believe we covered what I intended to do for this lecture. In conclusion, this lecture introduced the directional control valve, an essential fluid power component that stops, starts, and changes flow direction, ultimately influencing the actuation direction of a fluid power actuator. We discussed the construction and operation of directional control valves, examined common schematic elements associated with directional control valves, like positions, ways, actuation methods, return springs that center or offset the valve, manual overrides and detents, applied various directional control valves to circuit examples, examined the cutaway view of a spool-type directional control valve, discussed the operation of Poppet-style directional control valves, and examined representative performance curves on a datasheet. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.